Hi, good morning. It is a very cold day here in Boston. It is minus 1,000 degrees Fahrenheit, and I'm very glad to be in here recording a lecture in my nicely heated office. Today, we're going to continue with Reconstruction attacks. We're going to cover the second part of linear Reconstruction attacks, which is going to show how to reconstruct with fewer queries than what we saw last time. So I'll start by recapping last time a little bit and then talk about the main result for today. And then in the second video, we will come back and talk a little bit about computational issues with the attack and how to apply reconstruction attacks like this in practice. So to recap, we took a data set. We kind of took a realistic looking data set and we stylized it like what you see on the top right as a data set where each record consists of some kind of public information that can identify an individual, which we call Z, and some secret bit S that the attacker is trying to learn. And of course that the data analyst would like to get some statistics on. And we looked at something called count statistics or linear statistics, sometimes called statistical queries. And a query of this form is defined by some function phi that maps an identifier to a true-false value. And the value of the query is the sum over all of the records in the data set of phi applied to the identifiers times the secret bit. So another way you can think of this query is that phi selects a subset of the records based on the public identifiers and asks for the number of people in that subset who have their secret bit set to 1. And just for orientation, the way that we've written the queries, their answer is a number between 0 and n. So when we talk about accurately answering one of these queries, we want to answer it with error that is small. So ideally 0, but importantly much, much smaller than n. And the reason these are sometimes called linear statistics is because each query can be represented as the dot product between the vector of secret bits, which is what's on the right, so the vector of secret bits here, and the vector which says for each record in the data set, does phi evaluate to 1 on that data set? So you can think of this as being an indicator vector that says which of the records are in the subset and which are not. Okay, so what this means is that this model lets us ask kind of queries of the form, tell me the inner product between the secret vector S and some vector F that we're going to choose. Okay, and looks like it got cut off at the bottom of the slide, but just remember that we're going to talk about reconstruction from noisy answers to these queries. And so an answer is kind of accurate to a non-trivial degree if the error is much, much less than n. But we'd, of course, like answers where the error is not just less than n, but very small, like on the order of 1, let's say. And last time we proved the following theorem. Sorry, I'm still getting used to where my video goes in the corner and where I can't write. So it said, suppose we've somehow allowed queries for all 2 to the n vectors f. So the set of count statistics we're releasing is rich enough that it gives me the inner product of the secret vector s with every one of the 2 to the n possible vectors in 0, 1 to the n. And let's suppose that for each one of those 2 to the n queries, we got an answer whose error is at most alpha times n. So alpha is something small, maybe 1 over 1,000. Then the reconstruction algorithm we saw allows you to reconstruct the secret vector with error at most 4 alpha n. Okay, so for example, if all the queries are answered with error 0, we reconstruct the secret vector exactly. But if all the answers are given to us with error at most n over 1,000, we get n over 250 wrong at most. All right, and since reconstructing with error, much, much smaller than n means that we have recovered most of the secret bits, we're only wrong on a small fraction of secret bits, it means that if we try to answer every query with error that's much, much smaller than n, we're going to reconstruct with error that's much, much smaller than n. So if you give me answers that are even just a little bit non-trivially accurate, I'm going to reconstruct much better than random. So I'd suggest, if you're not sort of remembering the kind of ideas that go into proving this, maybe go back and watch the last video to refresh. I'm going to start from scratch, but if you're really not sure how to, what the ideas that go in, it might be good to warm up before getting into the new theorem we're going to present. Okay, so what's the new theorem we're going to print? So first of all, why would you hope to improve on this theorem? Well, this theorem already tells us something important, but maybe it's not that relevant in practice, because if you have a data set of size, let's say 100, 2 to the 100 queries is completely unreasonable, both in terms of how many statistics someone might try to release, and also in terms of how much time you have to do the reconstruction. So, we'd like to know what happens when you answer just a kind of modest number of queries. And the theorem we're going to look at today is a version of this theorem that applies to a small number of queries. So let's first look at what's different about the theorem. So first of all, instead of asking all 2 to the n possible queries, we're going to ask O of n random queries. So a little bit bigger than n random queries. So I think it depends exactly how many queries you want to ask, but think 2n, 10n kind of queries. So many fewer queries, that's good. And we're also later going to return to make the attack run in polynomial time. So not only are we going to have a small number of queries, but we're going to have an efficient way of doing the reconstruction. But what do we trade for that? Well, we're not going to be able to reconstruct with the same error. Instead of getting error proportional to alpha times n, we're going to get error proportional to the square of alpha times n. Okay, so what that means is that we're going to need alpha to be much smaller before we reconstruct accurately. And the way to think about it is we're trying to reconstruct n bits. And so we've done the reconstruction successfully when the reconstruction error is much, much smaller than n. So when is alpha n squared much, much smaller than n? Well, it's smaller than n when alpha times n is much, much smaller than root n. So this reconstruction attack is going to work whenever the queries are answered with error much, much smaller than root n. And there's some really interesting things about that root n bound, but I'm just going to make one point, which is that what this says is if you want to answer even order n random queries, then you have to add a pretty significant amount of error, right? You can't have error like plus or minus 5. You have to answer these counts with error plus or minus root n, okay? Which is, it's clearly like a significant amount of error. In particular, if you think of the data set as being kind of sampled from a population and you know a little bit about statistics, the kind of error that's already in the data set from sampling is itself kind of on the order of root n. And so what this says is that the error that you have to introduce is sort of significant enough that it can't just be thought of as statistical noise. That's a more fine point. You may not have the kind of context for interpreting that statement. We'll get into it more later, I hope. But that's just a thought if you are familiar with some kind of statistical things. And looking ahead, one more feature about this theorem is we're going to prove it for random queries, but what we'll see later is that it's not really important that the queries are random. What's really important is that the queries are sort of diverse enough in a certain sense. And random queries have that property, but we'll come back to talk about what do we really need from the queries when we get into practical attacks. All right, so we're going to spend most of the rest of this video just proving this theorem on the bottom. I should remind you this, both of these theorems are due to a really influential paper of Dina and Nissim from 2003 that sort of launched this line of work on differential privacy. And there's been a lot of work on reconstruction attacks since, but this theorem I'm going to present at the bottom was kind of like the theorem that really got this line of work going, so it's a very important theorem. And its proof is a little tricky, so I'm going to try my best to make it kind of accessible but and communicate the main ideas, but there's some technical parts of the proof that you may need to spend a little time kind of wrestling with. So let's sort of get into how we're going to prove the theorem. Okay. So, I'm sorry, I'm having a little trouble with my, I think I slightly misinterpreted where the bottom of the screen was because I had my little page guy on when I was writing these. So let me put it on so things stop getting cut off. So first of all, let's refresh our memory about the reconstruction algorithm itself. So if you look kind of here, so what does the reconstruction algorithm do? All it does is I tell you a set of k queries that I've issued, and I give you a corresponding answer to each of those queries, possibly with some noise. And what the reconstruction attack does is it's going to find some s tilde that is plausibly the true vector of secrets that gave rise to these answers. So what does that mean? Well, it's going to find the vector s tilde such that if I look at the maximum over all of the k queries, the difference between the true answer if the secrets were s tilde and the answer I got is minimized. So minimizing this fi dot s tilde minus ai. Okay, so what is that quantity? That quantity, right, so this quantity right here is the error that ai would have if the true secrets were s tilde. Okay, and then it's just going to output the s tilde that minimizes this. Okay, so the reconstruction attack is just finding the s tilde that's kind of closest to what is indicated by the queries and answers I have. Now, we want to show that this reconstruction attack is going to work in the sense that if all of the queries have error at most alpha n, we want to show that the reconstruction error will be proportional to alpha squared n squared. So to that end, I'm going to draw a little pictorial representation of all of the possible secret vectors s tilde that we could output in 0, 1 to the n. And of course, one of those is the true vector of secrets s. And we can divide up all of the possible vectors s tilde into two sets. There's the good ones drawn in blue that are close to s, and the bad ones drawn in red that are far from s. And in particular, close means they differ on less than alpha squared n squared coordinates. I put in sort of a magic constant of 1,000. That can definitely be improved. I'm not going to pay too much attention to exactly what the constant is, but the point is that there is some constant hiding here, and there's some fiddliness in trying to optimize it. So I'm just going to define good as less than 1,000 alpha squared n squared coordinates, because that I know will make the proof go through. Okay, and then so the blue are good. They're the ones that are close to s, and the red are bad. And what we'd like to show is that we're not going to output any of the choices of s tilde that are bad. Okay, that's like the key thing we want to show. We're not going to output any s tilde that's bad. Okay, so how are we going to show this? Well, what we're going to do is we're going to argue that random queries kind of eliminate a lot of bad choices of S tilde. So what do I mean by that? So get my pen out. So what I mean by that is that every kind of bad choice, every query we ask is going to tell us that some choices of S tilde can't be S. So they're going to reveal that like these can't be S and these can't be S, and the next query is going to reveal that these can't be S, the next one's going to reveal that these can't be S. And over time, once we have enough random queries, we'll get that we've eliminated all bad choices. So, intuition, every query eliminates some bad S tilde, and so enough queries will eliminate all of the bad S tilde. And so therefore we'll be left with a good S tilde. Okay? And in particular, an important thing to notice is that there's one kind of S that will never be eliminated, and the observation is that if all queries have error at most alpha n, then the max error, by definition, for the true secrets S is at most alpha n. So what we know is that this reconstruction attack is going to output some S tilde satisfying where this quantity is at most alpha n, because it can only output something that's at least as good as S itself. Okay, so because of the error, it might actually output something that's not S, where this quantity is even lower, but we know that it's going to output something where the answer is at most alpha n. So that's going to be the key thing we use, that this reconstruction algorithm is going to output something where the maximum error for S tilde is at most alpha n. Okay, so let's define some terms. Okay, so statement 1, S tilde will satisfy max I fi S tilde minus ai at most alpha n. Okay, so we know that alpha S tilde will satisfy that condition. So we want to show that any S tilde that satisfies this condition can't be a bad S tilde. Okay, so let's say that we have to define a term here. So let's say that a query fi, sorry. Okay, so S tilde is eliminated if there exists fi such that fi dot S tilde minus ai is bigger than alpha n. Okay, so we know that S tilde can't be the choice if there's even one query fi whose error, where the error of S tilde with respect to AI, the error of AI with respect to S tilde as the true bit, as the secret bits, is bigger than alpha n. Okay, that can't be chosen. All right, and we'll also say S tilde is eliminated by fi. So we'll talk about which query eliminated it. All right, and so now the goal is we will show that for every bad S tilde, some query eliminates it. with high probability. Okay, and now when I say with high probability, what I mean is that this is going to hold if we've chosen good queries. So we're choosing random queries. We could, of course, get unlucky and choose queries that somehow don't help us figure out what S is at all. But we'll show that if we choose random queries, then it's very likely that we'll get a set of random queries that has the property that it eliminates all of the bad S tildes. Okay, so I need like one more page here. All right, so what do we want to do? So we want to bound the probability that there is some bad S tilde not eliminated. Okay, so we want to show that that's small. We want to show that every bad S tilde has been eliminated. Now, an important probability fact is that this is at most the sum over all of the bad S tilde of the probability that S tilde is not eliminated. Okay, so if we can show that every specific bad S tilde is very, 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 very unlikely not to be eliminated, we can sum up over all of the bad tildes. And notice, there can only be 2 to the n bad tildes, right? There's only 2 to the n tildes in total, so there can only be 2 to the n bad ones. So this is at most 2 to the n times the probability that S tilde, that an individual S tilde is not eliminated. And notice I'm being just a little bit sloppy with how I wrote this statement, because this should really say, for the least likely. This is kind of for the worst S tilde. So I'm saying if we can show that for every S tilde this quantity is small, we can just multiply the quantity by 2 to the n and upper bound the thing we want. All right, and so what we're going to do is we're actually going to show that that this thing is at most like 2 to the minus 2n. The probability that each individual bad S tilde is not eliminated is like 2 to the minus 2n. And that means that the probability that some S tilde is not eliminated is very, very small, like 2 to the minus n. And here, this is going to be assuming something like 20n random queries. Okay, so this is going to be, we pick an S tilde, and we choose 20n queries at random, and we'll conclude that the probability that that S tilde is not eliminated is extremely small. Okay, so all of the work is really in like bounding this quantity that some bad S tilde is not eliminated. Okay, so now let's see what that proof looks like. Well, we want to bound the probability that some S tilde is not eliminated. And that is the probability that for every single query we ask I, S tilde is not eliminated by the query fi. And the important thing is that the queries are random and independent. Okay, really, really important. Like the queries are not only random, but they're independent from one another. So the event that S tilde is not eliminated by query 1 and S tilde is not eliminated by query 2 are independent events. And that means that the probability that S tilde is not eliminated by any query is the product of the probability that it's not eliminated by each query. Okay, and remember, k equals number of queries. Okay, so the probability S tilde is not eliminated is the probability that S tilde is not eliminated by some specific query Fi to the power of k, where k is the number of queries we ask. Okay, so as we take more queries, this thing is going to be hopefully going down exponentially. Now, what is the event that S tilde is not eliminated by Fi? Well, it's the event that for that particular query, sorry, I made a mistake here. So it's the event that for that particular query, sorry, I keep making mistakes here, that the error, that the difference between the answer to the query on S tilde and on S is at most, let's say, 4 alpha n. Okay, so the only way that S tilde cannot be eliminated is if Fi gives close answers on S tilde and S. And now, the magic is that that quantity is at most, that probability is at most 9/10. So what I claim, the key lemma, the like very not obvious key lemma, is that if S tilde is bad, meaning S tilde is far away from S, then for a random query, the probability that the answer to that random query on S tilde and S is within, let's say, 4 alpha n, is at most 9/10. It's not 1. Like it can't happen 100% of the time. It can't. There's like some non-trivial chance that this query shows that S tilde and S are far apart. All right, and now we have that for each query, it's eliminating S tilde with probability. It fails to eliminate with probability 9/10. So if I take k to be, let's say 20n, then the overall probability that S tilde never gets eliminated is going to be going to 0 very fast. It's going to be 2 to the minus 2n. Okay, and one thing that's important to note, right? Why does this mean that it's eliminated? Well, if you kind of think about what this looks like on the line, this says that if this is FIS and this is FIS tilde, and they're at least 4 alpha n apart, and this is AI, and it's at most alpha n from SIS, then clearly with respect to this query, the error, right, so this error, this is at most alpha n, and so that means that this is at least 3 alpha n, which says that S tilde will have to have larger error than S, so it can't be chosen by the reconstruction attack. Okay, so remember, the definition of eliminated says that fi.s tilde is far from AI, but since AI is close to fi.s, the thing that I wrote in the probability also implies that S tilde will be eliminated. Sorry, that was a bit of a mouthful, but hopefully the picture makes it clear. Okay, but the big thing is we have to prove this key lemma, all right? And proving this exactly is actually going to be a little bit like beyond the scope, so let me just kind of give you the intuition for how you prove the key lemma. I'm not going to prove it exactly, but let me give you the idea. So here's the key points. So the thing I want to prove, like the key lemma in the abstract, says the following. It says, suppose that S and S tilde are vectors in 0, 1 to the n, and they differ on m coordinates. Okay, so in our example, m is going to be about alpha squared n squared, but in general, just let them differ on m coordinates. And f is a random vector. Okay, then what the lemma says is that the probability that the difference between f dot s and f dot s tilde is smaller than about square root m can't be too large. Okay, so I have this random variable. This probability, s and s tilde are fixed. This probability only involves the choice of f. And it says that the probability that f dot s and f dot s tilde are closer than square root m is significantly smaller than 1. Okay, it might make it a little easier if you think, this is equivalent to probability that f dot s minus f dot s tilde is bigger than square root m over 10 is bigger than 1/10. Okay, so this says there's like a non-trivial chance that these f dot s and f dot s tilde differ by about square root m. Okay, and these constants are also a little bit made up and are probably not optimal, but for the theorem, as I stated it, it's enough to just show that it's kind of the difference is on the order of square root m with any constant probability. You can definitely make these constants stronger if you work at it a little bit. So let me give you the intuition. So let's fix s and s tilde and let t be s minus s tilde. All right, so then notice that t can have 3 types of entries. Every entry can be -1, 0, or 1. And t has m non-zero coordinates. Okay, so t is some vector whose entries are +1, -1, and most of the think of most of the coordinates as being 0. There's only m non-zero coordinates. Okay, so now t is fixed and f is random. So at this point, f dot t is equal to the sum over j equals 1 to n of fj times tj. All right, and this is equal to the sum over all the non-zero tj of fj times tj. All right, so all of the ones where tj is 0 just kind of don't matter. And what we have is a bunch of coordinates where, we have a sum of m random variables of the form either fj or minus fj. Okay, so let's look at what those random variables actually look like. So if tj equals 1, then fj tj equals 1 with probability 1/2 and 0 with probability 1/2. And if tj is -1, then it's the same thing but reversed. Okay, so in this case, the expectation of fj tj is equal to 1/2. And the variance, if you're familiar with your binomial random variables, is 1/4. All right, and again, the same thing is true if tj is -1. Now the expectation is -1/2, and the variance is 1/4. Okay, and importantly, this is a sum of independent random variables. Okay, and here's where I'm going to do a little sleight of hand and just give you some intuition and not give anything like a rigorous proof. Sums of independent random variables behave like Gaussians. So what does that mean? So first of all, let's note that the variance of f times t equals the variance of sum of the non-zero tj of fj tj. And because they're independent, that's the sum over the non-zero tj of the variance of fj tj. And that is m over 4. So the variance of this random variable is going to be m over 4. We don't actually know its mean because it depends on whether the tj's are +1 or -1. But the important thing is that the variance is m over 4. All right, and so let me start by just saying that intuitively, what does it mean that the variance is m over 4? It means that the standard deviation is square root m over 2. And that's where this comes from, basically, right? The standard deviation is on the order of square root m. So intuitively, random variables that have a standard deviation of square root m should have like a decent chance of being one standard deviation away from their mean. And the only problem is that that's not always true. Like, you can construct random variables whose standard deviation is root m, but they're very unlikely to differ from their mean by as much as root m. And the important thing is that that can't happen for sums of independent random variables. So the important thing is that sums of independent random variables look kind of like Gaussians. So if this is the mean, and this is 1 ± 1 standard deviation, then sums of independent random variables look like this, and they have kind of a decent chance of putting mass 1 standard deviation above the mean. And more generally, if you look at any interval whose width is about 1 standard deviation, the distribution doesn't put too much mass on that interval. Okay, so that's very, very like hand wavy. We can, in the notes, there's also currently sort of this hand wavy proof, but if you'd like, I can go into it more later in lecture. If you're a little bit in doubt, try just like picking a vector t with m non-zero coordinates and choosing a random f and plotting the distribution, and what you'll see is something that looks vaguely Gaussian, provided that m is big enough. So like set m to be 50 and just kind of see what happens, and you'll see that this picture really happens. Okay, but going back up to the top of the slide, the intuition for this claim is that this vector, this quantity f dot s minus s tilde has standard deviation about root m, and so it has a significant probability of being 1 standard deviation from its mean, or in this case, more like 1/5 of a standard deviation from its mean. Okay, so that's the key lemma. Again, it's a little tricky to rigorously prove this because you have to understand this connection between sums of independent random variables and sort of Gaussian-like random variables. You can prove this using something called the Paley-Zygmund inequality if you want to look it up, but it's going to be sort of why this is true. It's more important to understand it at this level that I'm describing it. Okay, good. So we proved the key lemma. Let's kind of bubble back up and look what we did. We said that for every bad vector s tilde, the probability that it's not eliminated is very small for every individual s tilde. The reason that was useful is because it allowed us to prove that every bad s tilde is not eliminated. And the reason that's useful is because it shows that the error of the reconstruction can't be worse than about alpha n, or sorry, it shows that a good s tilde is chosen, and sort of by definition, a good s tilde is one that is within alpha squared n squared of the true s, which is the bound we wanted to show. Okay, so that gives us the theorem we wanted. If we ask O of n random queries, and all the answers have error alpha n, then the reconstruction error is at most alpha n all squared. And in particular, if the error on the queries is much smaller than root n, we'll reconstruct accurately. Okay, and so the thing that you want to remember, the thing that's going to come up a bunch of times later in the course, is that answering O of n random queries requires at least root n error, or else reconstruction can happen. So what are we going to do in the next video? Well, first I'm going to talk about how to make this attack polynomial time. So far we've just used a polynomial number of queries, but we haven't made the attack polynomial time. And then what I'm going to do is talk a little bit about how this model of attacks applies to kind of real systems for releasing statistics, and how challenging it can be to sort of avoid these types of attacks, even though the theory is a little bit specialized to things like random queries. So take a break, stretch out, and come back for the next video.